Okay, so your homework last night was just to fill in this review chart here, just to sum up everything we've done with plate tectonics and continental drift. If you did struggle off the top of your head, which, like I said, it was what your quiz was on Tuesday. Now my page is blank, but your page 11 literally had everything you needed on it. So what I was asking is, divergent plate boundaries are where two plates do what at divergent? Move apart, yes. At every divergent plate boundary we've ever looked at, so divergent boundary, divergent boundary, divergent, divergent, more over here, what is formed at every divergent plate boundary? That is a ridge. And give me an example. You could have either told me the name of a ridge or two plates that are diverging. I'm going to go with just picking any ridge. I'm going to go with the Mid-Atlantic Ridge. And then we could go to transform plate boundaries. What happens at transform plate boundaries? These guys. Everybody's talking. Slide past each other. And that forms a fault. The most famous example is the San Andreas. That left the only one missing. So we had divergent, we had transform, we were missing convergent. And that's where two plates collide or go together. There are three types of convergent plate boundaries. Where two oceanic plates collide, where an oceanic and a continental plate collide. We were missing two continental plates. We'll stick with this one. When that happens, there's no subduction and we form mountains. The best example straight from our notes is the Himalayan mountains. And before anybody teases me for not knowing how to spell them. Himalayan. Then we can pick a different one where an ocean and a continental plate collides. This occurs with subduction and the formation of a trench and mountains. Best example of this is the Andes Mountains, where South America and the Pacific Ocean in the form of the Nazca Plate are coming together. We get the Peru-Chile Trench and the Andes Mountains. So actually I should probably add that. So the Andes Mountains and the Peru-Chile Trench. And then finally we have where two oceanic plates collide. Again, we get subduction and this forms a trench and underwater volcanoes. And the perfect example of this, there's a bunch of them, but we could go with the Mariana Trench or the Aleutian Trench, either one. So that should have not stumped any of you and should have only taken what that was, 5 minutes, if that. It stumped you because you forgot to turn to that page and do it. Yeah. So if you do forget to do your homework, it's okay. It's not the end of the world. This was just a small homework assignment, but this is not even close to a quiz grade. So, all right, we are moving on then. So we've talked about how plates move, why plates move, what happens when they move. Now we're going to be focusing in on earthquakes. So before we start earthquakes, since like we talked about at the beginning of this chapter, most of us have not lived through a substantial earthquake. In fact, nobody said they did. A few of you noticed the one last year, the small guy, but none of us have really been through like a truly earth-shaking earthquake. So let's just watch some other people's experiences first. So I think this one should be decent. Jack, while you're over there, you mind turning the lights off? All right, let's see what this video has to teach us.
From above, the planet appears eerily still. From above, the planet appears eerily still. But every mountain range and every chasm on its face is a scar, with many telling a story of when the Earth rumbled to life. Earthquakes occur around the world. They've been recorded on all 7 continents, but most quakes take place in just 3 regions. The Mid-Atlantic Ridge, an underwater line that runs down the Atlantic Ocean, the Alpine Belt, which stretches from the Mediterranean to Southeast Asia, and the Circum-Pacific Belt, which traces along the edges of the Pacific Ocean and is where about 80% of all earthquakes occur. These areas experience the most earthquakes due to what lies beneath the surface. Earthquakes are the result of pressure, specifically pressure caused by extreme stress in the Earth's crust. That stress can be caused by volcanic activity or even man-made activities in certain areas. However, most earthquake-inducing stress is caused by the movement of tectonic plates. Tectonic plates are constantly moving, either against, away, along, or underneath each other. But sometimes their edges may catch and stick. The plates, however, continue to move, or at least attempt to. Energy from this attempted movement builds around the edge's sticking point, creating immense pressure until the edges are forced to let go and the plates slip. This causes a sudden and powerful release of energy, so powerful that it breaks the Earth's crust. This fracturing emits shock waves through the ground and causes intense vibrations, or quakes. In fact, the world's most earthquake-prone regions are where the most geologically active plates meet. Earthquakes, or any seismic activity, are recorded by seismographs. When the ground shakes, seismographs oscillate, drawing a jagged line to reflect this movement. The more extreme the earthquake, the greater the height of the jagged line. These recorded motions are then used to measure the earthquake's strength, or magnitude. While several scales of magnitude exist, the one seismologists prefer is the moment magnitude scale. It has no upper limit, and it measures earthquakes logarithmically. This means that each magnitude on its scale is 10 times greater than the one before it. Unlike the now rarely used Richter scale, the moment magnitude scale can be applied globally and can measure quakes of the highest magnitudes. The largest recorded earthquake occurred near Valdivia, Chile in 1960. Nestled within the Circum-Pacific Belt, the Valdivia earthquake was the most powerful in a series of quakes that struck the region, measuring at a magnitude of about 9.5. In addition to causing devastating tremors on land, the earthquake also generated a deadly tsunami reaching up to 80 feet high. The tsunami raced across the Pacific Ocean, hitting faraway countries like the Philippines and Japan. In fact, data from seismographs showed that the shock waves emitted by the Valdivia earthquake continued to shake the entire planet for days. Some earthquake-prone areas have adapted various ways to protect their communities. Buildings and bridges are designed to sway rather than break when an earthquake occurs. The public is educated on how to protect themselves during a seismic event, and government officials enact drills to ensure the protection of their people. Earthquakes can leave behind incredible devastation. But these same forces have also created magnificent features, with each adding character to a planet so unique.
All right, that was a good little introduction. Okay. So we're gonna go to our notes and start learning some basics about earthquakes. I will tell you, oh, of course I had these already filled in. I will tell you that we are now entering what I call, or I believe is the hardest thing we're going to do all year. Why do we have to do it? Because New York State says you have to, and it will be on your regents. Good news, not for you, but for my future students, this is not part of the new standard. So, what? Not kidding, but, the new standards aren't a peach either, but they will get rid of this one, thing. It'll be added, something else will be added in its place, I'm sure, but this is not part of the new standard. So like I said, I do think this is the hardest thing we've done all year. But I will also say, because it's the hardest thing we'll do all year, I've become, over the last 17 years of teaching, really good at teaching it. I will toot my own horn and say, I'm really good at teaching this chapter. And the reason why I'm really good at teaching this stuff is because when I started, I had no idea how to do it. I had to teach myself how to do it before I could teach my students how to do it. So I've gotten really good at it. Yeah, Nick.
I wonder why the natural news actually was like, yeah, many people are dying, but like, look what it made.
Yeah, but look what it makes. It's really pretty. Yeah, well, there's that too. Yeah, I mean, it depends on how you look at the situation. I think she's just trying to point out that these huge forces, while even though they're devastating, they can be amazing as well. And it just makes us appreciate where we live, where we don't have them, at least. So let's start with earthquakes. From the video, what is an earthquake, or from your real life experience? Plates crash into each other and I cut you off, I'm sorry. Okay. And what do they cause? The earth to shake. So what is an earthquake? It's literally just the shaking of the earth's crust caused by a release of energy. This video talked about some potential causes for that energy. Where does that energy come from? They actually mentioned 3 different things that can cause that energy to be released. One, what was Dakota? What did you just say caused earthquakes? So the first and most obvious cause of earthquakes are the plates. Yeah. Man-made. So I don't know if you saw what they were talking about in that video, but it was some sort of drilling equipment, probably drilling for gas or oil. Yeah. And then the other one was a volcano. Yeah. So I'll put that up there, and then I'll just talk about that drilling equipment. I also put up meteors there. So if a giant meteor was to hit the earth, like it did with the dinosaurs, or even not too long ago, a small one hit, I believe, in Siberia. And we were able to record that on our seismic recording stations. With the, so I did put up nuclear explosions. I guess I forgot to put up the drilling stuff. A few years ago, when they were drilling for oil in places where there hasn't been oil drilled before, it did end up causing some small little earthquakes because it just caused a release of energy while they were doing it. During the Cold War, they used earthquake monitors to see, and even still today, with like Oh God, here's where I'm gonna sound stupid. Is it North Korea that's the bad one? Okay, so we might, sorry, okay?
North Korea is the one that changed,
So that's what happens when you're not that involved in the social studies department. But anyway, they still monitor North Korea's activities with nuclear testing and things like that by monitoring our earthquake machines, our earthquake monitors. Because you can feel the earth shaking from those explosions, even if you couldn't see them. So they can pick up those tiny movements across the world, even if we can't actually physically see them happening. Yeah. They test them more often than you think. I know like North Korea was getting in trouble for testing them when they weren't allowed to. So we haven't, I don't think, in the United States in a while, but not the right class. What damages can happen because of earthquakes? Obviously, what's the most obvious damage? Buildings fall down. What other that word? Yeah, that. What other types can be damaged though? Like what other issues will there be other than buildings and bridges collapsing? There are obviously casualties, yep. What'd you say, Kim? Okay, the earth can literally change. Did you say wildlife too? Yeah, so that's all gonna be affected. But after an earthquake, some of the unthought about things would be there's gonna be some fires and there could potentially be water shortages. Well, how can an earthquake cause a fire? What do you say, Dakota? That's the most common. So no, it's not the friction causing enough heat to cause a fire, but it really comes down to power lines, gas lines. I mean, even if something as simple as a lamp falls over, a spark happens, you can end up with a fire. Or, I mean, obviously, if a candle falls over, you can end up with a fire. But in addition to power lines being down, you also might have broken gas lines or broken gas tanks at the gas station. You can imagine how much damage could be caused when fire meets gas. Yeah, that means big damage, big fire. What about water shortages? How could earthquakes cause water shortage? Yeah, TJ, what are you thinking? Okay, so first of all, any pipes you got going, they could break. Yeah. It could crack the water reservoir, causing some leakages and not being able to deliver it to the people.
I actually, makes them go away, and earthquake then continues away.
I'll have to look that one up. So there's also one more thing. So even if your water line might not be damaged, this one kind of applies to us around here. Where do a lot of you guys out here get your water from? Okay, so some of you get it from the town, but a lot of people have wells. And there's also a lot of farmland here. What do, especially those dairy farms, have a lot of? Cows and cow poop. And how do they store the cow poop? You ever seen those big giant beautiful swimming pools filled with cow poop? They're not really swimming pools. Big, I don't know what they're called, but have you seen them? It's not a silo, but like a new manure pit. It's like a big giant swimming pool that they put their liquid manure in. There's ones all over every cow farm. I'll wait till Sam comes in. Okay, remind me of that in a minute. Those. What happens if an earthquake happens? You got one of those filled to the brim with some lovely cow manure. Uh-oh. Where's that cow manure going? Okay, everywhere. Not just cow manure, but what about your own sewer lines? Uh-oh, those break. Then we got sewer, cow poop, sewage, mixing with, the groundwater. Yummy. So that sounds awful. I would assume in places that are prone for earthquakes, that, those, say, what are they called again, Taylor? Slurry stores. I bet they're reinforced out in California, or potentially even have different methods in places where that they're ready for an earthquake. Same with even things like gas tanks are regulated differently in different places. Gas tanks, like the underwater ones for or underground ones for gas stations, they're regulated differently for different places due to the potential of earthquakes, just like that building stuff they were talking about on there. Our houses don't have to be earthquake proof because we're not in an earthquake zone. California houses have to be earthquake resistant at least. Dawn, you were gonna add something? Mm-hmm. Right. Right. So out here, we don't have those buildings that are designed to sway as much because we don't have it obviously costs more, but it's worth it in California where they could fall down. Here, we take the risk of we're not going to have a big earthquake. Yeah. What? Mm-hmm. Yes, then they do that for hurricanes and stuff too.
I believe they did the same thing.
I don't think there's a big draw for tall buildings in Yorkshire too much. I mean, you never know down the road, but you have one. You could have one, but then you know what the next problem is? Then Yorkshire would need a hook and ladder truck for their fire department, which would then cost a couple $1 million. So all of that has to be taken into consideration when they're planning stuff. So you would need a bigger type of fire protection to take care of those buildings, like not a well. I think that all goes into planning. What's up? What do you guys say about the fire company? So does, is it Boston Colden? Somebody has one over in that area. So there are a few hook and ladder trucks, but one in all of the county isn't enough if you're going to, like, New York City has those hook and ladder trucks practically probably on every corner, or at least really close to every corner. All right, so a couple earth science vocab words here. So the focus is a new vocab word for you. You've probably never heard it before in this case, obviously, or in this context, I should say. So a focus is located underground where the actual movement of the plates occurs. So this is really the earth science-y definition of where the earthquake happens. So it could be close to the surface, it could be deep underground, but again, this is underground. Versus in the video, or maybe you've already known this word. Have you guys heard the next word before? Epicenter. You've heard it. And in really all that is, it's located on the Earth's surface directly above the focus. In other words, most of us, when we say, hey, where was the earthquake? We don't care so much how far underground it was. We want to know, hey, what city was it in? So an epicenter is really telling you the name of the place the earthquake happened. We will focus more on the word epicenter, but do notice the difference between the two. So the epicenter is on the surface, focus is underground. And then finally, hopefully you can answer that last question yourself, or that last bullet. Most earthquakes and volcanoes occur at or near, not just plates, but plate boundaries or the edges of plates. Fault lines work as well, but we do use the phrase plate boundaries. So just be careful, Dakota, your answer, I knew what you meant, but please don't answer that by saying at or near plates. Because again, plates cover the whole earth, but the earthquakes and volcanoes happen at the boundaries or the edges or where the two plates meet. So there's a little difference in the words there, and that would be the difference between getting it right and wrong. Literally on the regions, if that was a question, it would say, do not allow credit for the response near a plate, because the whole world is near a plate. We need plate boundary for that. All right, then you got a picture. Oh, you got this picture in your notes, right? It's right there below it. I just would like you to label the one that's near the surface. That's going to be the epicenter. And then the one that's deep underneath the ground, that's going to be the focus. All right, for the remainder of class, we're going to learn a little bit about those different waves that come through when there's an earthquake. So they mentioned that the waves get sent out from the earthquake. They said that one in Chile, those waves cause the world to shake its head for days because it took days for some of those waves to travel all the way across the earth. So what waves are we talking about? We're not there yet. All right, so we're going to go to page 17 and page 19. So we've done things like this before. I'm going to hand out some highlighters for anybody who wants a highlighter. But we're going to be reading page 17. You can see there's not actually much reading there. And then these are our notes about earthquakes. So in this, it says we're going to complete the table using the reading. We're going to be comparing what's called P waves to S waves. So we're going to be looking for the actual names for P waves. So they're not just called P waves, they have a real name. Same for S waves. There's a speed, and in parentheses, I put arrival at seismic stations. Tell me which one gets there first and which one gets there second. The movement is described in the reading. So how do they move? If you want to hold off on drawing a picture till we make sure that's correct, you can hold off. And then types of matter the wave can travel through. What do I mean by matter? Solid, liquid, or gas. So we're looking for 8 or what is that? 1, 2, 3, 4, 5 technically, but 8 because you don't have to do the picture right away. Explanations from the reading. Anybody want a highlighter who doesn't already have one? How about this? Don't write anything on page 19 yet. Just go find it in the reading. If you already did, I'm sure you didn't do it wrong. Now, who needs a highlighter? You did? Highlighter? Okay, go. Sorry, I guess you're underlining them. Highlighter, anybody? Either highlight or underline or circle the answers in the reading. Don't bother writing yet. Because I would hate for you to fill that page in and then have to change it if you got something wrong. Nobody else wants a highlighter? Not gonna let me throw this at anyone else? I do, especially from. Nice. Okay, you can highlight it. You got one. Very cool. So again, in case you're confused on what I'm asking of you, you're going to be looking for these answers in the reading and just go ahead and highlight them. Hint, for example, P waves or primary waves. That's the first thing you should be highlighting. Oh, and yep, it's on there. S waves are secondary waves. There, I gave you 2 answers. I know, you probably already figured that one out. So go ahead and highlight and look for the rest of the answers. So I'm going to go ahead and rip this page off just to make my life a little easier. You are welcome to do so as well, or you can just leave it in there. So as we stated already, what is the name? The real name for P waves, they're really called primary. So if you haven't already put that in your notes, go ahead and add it. So it's primary waves for P. What are S waves really called? Yeah, those are secondary. And from the reading, did we find the speed or when they arrive at the seismic station? Primary arrive first. So where was that? P waves are the fastest kind of seismic wave and arrives at the seismic station first. So let's put both of that in your notes. Their speed is fast, which means they arrive first. And then how about the S waves? They are. So S waves are the second wave you feel in an earthquake. An S wave is slower than a P wave. So S waves are slower, which means they arrive second. Just before anybody gets thinking this, have you guys heard of aftershocks? That's not an S wave. So an aftershock, so they kind of showed it in the video, and I think I talked about it yesterday. As those plates are moving past each other, they're actually kind of stuck, and then all of a sudden they slip. Well, what happens is then they are kind of loose and wiggly, and so there might be some more earthquakes until they kind of get stuck again and find like another place where they can live happily for many years. So a secondary wave, actually a P wave and an S wave, they're both released the second those plates shift. Aftershock is its own little mini earthquake that comes afterwards, and it has its own P and its own S waves. So they're not P and S waves are earthquake and aftershock. They each have their own set of P and S waves. What was that? No? Nothing? Okay, just couldn't hear you. So describe the motion. How did they say that the P waves moved? Yeah, it pushes and pulls the rock it moves through. And it went on to say similarly to, and I don't know if I've ever heard thunder be quite this loud that it shakes. I guess I've definitely heard some rattling in the house. Thunder and lightning can cause some waves to happen as well, so much that it could wiggle back and forth some loose windows. That would have to be pretty intense. So in the picture here, it kind of shows what they mean by the push and pull. How many of you have had a slinky at least at one point in your life? Yeah, so you've had some slinkies. Now slinkies are cool because they go down the stairs. Have you ever actually gotten them to go down the stairs? Once. That's not the kind of reason I want to talk about a slinky. I want to talk about a slinky more for its springy ability. So with a slinky, if you were to hold it still at one end and you were to push the slinky forward like this guy did here, this hand did, and then pull it back, what you'll see is that push and pull motion travels down the whole slinky. So you can see here it's separated, here it's squished together, here it's normal. Now that pulled apart moves here and the squishness is there all the way down the slinky. So that's how a P wave travels, in that push and pull motion in the ground. What did they say about an S wave? Up and down or side to side? That's also shown here. This is more like those classic waves you might be thinking of when it just goes up and back down. So you take a string, you pull it up and you pull it down, and that wave will travel along the string. That's how it moves in S waves through the ground. So with the picture for the P wave, I'm going to show those squiggles with some of them being spread apart and then some of them being like practically right on top of each other. And the S wave, I'm just going to draw a typical, I don't know if that's a sine or a cosine, but that kind of deal, just an up and down hill. And then what type of material did it say? For P waves, that is solid and liquids. And how about S waves? Solids only. So obviously this is where we're going to end. I do want to point out how you can easily remember all of this stuff. Hopefully you notice. So for S waves, S waves, they are called S waves because they are secondary. They are slower. They arrive second. They move side to side. And you may have noticed, what does this letter look like? That's an S, and they only go through solids. So S waves truly appreciate their S's. All right, we'll pick up using that reference table tomorrow. No homework tonight.